In the last video, we looked at the nature of redox reactions. They're just electron transfer reactions. What we're going to look at in this video is a foolproof way to balance redox reactions. Most chemical equations we do by inspection, kind of trial and error. But I have a systematic way to balance redox reactions, which is going to help because sometimes the coefficients can get quite complicated. Now, the way I show you may not be the way you learned in high school. And as always, if you know another way to do this that works reliably for you, that you feel confident about, go ahead and use it. What I'm going to do is balance it by the method of half reactions. Now, technically, I can't divide redox into two halves. I can't have oxidation happening without reduction. But on paper, I can. And if I separate oxidation and reduction on paper, then it's going to make things easier for me. Now, I'm going to follow this set of steps, but I hope I'm going to chunk it into a logical order. And that way, you will be able to remember it. I am not going to provide this list to you later. I hope you see that you don't need it because when you practice, you'll become fluent. But I will apply these steps as I go through some examples on the following slides. So here is a redox reaction. Now, first of all, I have to know it's a redox reaction in order to be able to use this approach. A redox reaction is a change in oxidation number. And I see that this is because in my reaction, I see mercury 0, elemental mercury, and mercury 2+. So the charges are different, the oxidation states are different. This is a redox reaction and I can balance it by the half reaction method. So let's go to step 1. I'm going to separate the reaction in two half reactions. And how I'm going to do that is put all the chromium containing species in one equation. And all the mercury containing species in another half reaction. All right, that's step number 1. Now what do? I balance all the atoms except oxygen and hydrogen. So in the first half reaction with the chromium, I see 2 chromiums on the left-hand side, so I'm going to need 2 chromiums on the right-hand side. Now for the mercury half reaction, 1 mercury on the left, 1 mercury on the right, done. The oxygen isn't balanced yet for the chromium half reaction, but that will come later. All right, previous slide, next step. Number 3, we're going to balance the oxygen. Now, what are we going to use to balance the oxygen? I left a blank there so you could use some common sense. What is in the beaker that we're allowed to use? I've written these as net ionic equations and I haven't shown the states, but the default is that we're working in aqueous solution. So we're going to balance the oxygen with water molecules. All right, on to the next slide and we'll apply it. In the chromium half reaction, I see 7 oxygens on the left. So I'm going to have to add 7 waters on the right. And I'm going to check carefully at every step that it is balanced. It is so easy to make a slip of the pencil. And if you don't catch it early, it's going to be really hard to find later. Sometimes tell me they can't do this. Really, it's not the concept that's a problem. They've just made a slip of the pencil. So we're going to check early and we're going to check often. Let's double check. On the chromium half reaction, there's 7 oxygen on the left-hand side, 7 oxygen on the right-hand side. Good. No oxygen in the second half reaction with the mercury. Back to the next step. Number 4 says we're going to balance hydrogen. Now, what are we going to balance hydrogen? We're going to make the assumption that we're in acidic solution. So I'm going to balance hydrogen with H+. Sometimes we're not in acidic solution. But I'm going to balance it at acid first, and if it turns out to be in basic solution, I'll fix that later. I will tell you when it's in base. Don't worry, you'll see it. Now, usually when I deal with acidic solution, I use hydronium, H3O+. That's more correct, but this is the one time I'm going to stay with H+. And the reason for that is that if I use H3O+, I'll mess up the oxygen balance that I got in the last step. If I just use H+, I balance the hydrogen, and then I'm done. What I can see is a chunk of information, 2, 3, and 4 together. I can chunk in the idea of balancing the atoms. And the reason we do it in the order that we do is that each step we go is messing up fewer and fewer different kinds of atoms. In step 2, I balance everything but the hydrogen and the oxygen. Then I balance the oxygen, and that only messes up the hydrogen. So finally, I balance the hydrogen. So not really 3 separate ideas. One idea is balance the atoms. All right, let's apply that to the example we're working on. In the half reaction with the chromium, on the right-hand side, I see 14 hydrogens. So I'm going to balance that with 14 H pluses. Now check early, check often. 14 hydrogens on the left, 14 hydrogens on the right. Good. Mercury half reaction, no hydrogen, don't have to do that. So I've got the atoms balanced. Now what's the next step? Number 5 says we're going to balance the charge. And it is just as important to balance the charge as the atoms. Now these are redox reactions. They're electron transfer reactions. So I'm going to balance the charge with electrons. Where's my pen? There it is. So let's go back to our example. For the chromium half reaction, I'm going to count up the total charge on the left-hand side. 2 minus plus 14 pluses, 12 plus on the left-hand side. On the right-hand side of the chromium half reaction, I see 6 plus. So 12 plus on the left, 6 plus on the right. And the difference there is 6 electrons. I have to put 6 electrons on one side or the other. This is the part where I have to be most careful because I'm adding electrons. I'm adding negatives. So which side am I going to add 6 electrons to? I'm going to try adding it to the left. But remember, check early, check often. We want to make sure we did that to the correct side. Now the total charge on the left-hand side. -6 minus 2 is -8, plus 14 is +6 on the left. On the right, +6, good, we're balanced. Now for the mercury half reaction. On the left-hand side, the total charge is 0. On the right-hand side, it's 2 plus, so the difference between 0 and 2 plus is 2 electrons. Which side do they go on? I think they go on the right-hand side, and let's double check. Now, total charge on the left-hand side is 0. Total charge on the right-hand side is 0. Equal charge on both sides, the charge is balanced. Now, a beautiful thing just happened that should always happen. We have to transfer the electrons, so the electrons should go in to one half reaction and come out of the other side. If it doesn't happen, go back and check your work. All right, each half reaction is now balanced for atoms and for charge. Now what? Number 6 says, multiply each half reaction by an appropriate factor. What's an appropriate factor? Let's look at the example. In my final redox reaction, I should not see any electrons left over. I want to make sure that the number of electrons in on one side is the number of electrons out in the other half reaction. So what I need to do is find what the mathematicians call the least common multiple of 6 and 2. That would be 6. In other words, I want 6 electrons in on one side and 6 out on the other. So to do that, I'm going to multiply the second half reaction by 3. And that will give me a total of 6 electrons out the other side. Notice that I'm balancing it by multiplying the whole equation by 3. All right, what now? Number 7, add the half reactions together. All right, here we go. I'm going to add them all up. 6 electrons on the left-hand side plus dichromate ion, and don't worry, I know you don't know that's a dichromate, plus 14 H pluses, plus 3 mercury. Remember, we multiplied that whole equation by 3. On the product side, 2 Cr3 plus 7 H2O plus 3 mercury 2 plus 6 electrons. Now this time I brought down every species when I did the addition, but a chemical equation shows only what changes. So I'm going to cancel out what's the same on both. I'm going to cancel out the 6 electrons on each side, and that will make it tidier and easier to follow. So I'm just going to copy everything else down there. Two Cr3 plus 7 H2O plus 3 Hg2 plus. All right, we're in the home stretch. What now? Number 8, it's in red. It's the most important step. We're going to check that the reaction truly is balanced, both for atoms and for charge. Don't forget to check the charge. Now, sometimes it's hard to be confident with your answer, but this problem is beautiful. If your final reaction is balanced, you are right. Let's check. Final reaction, 2 chromium on the left, 2 chromium on the right, 7 oxygen on the left, 7 oxygen on the right, 14 hydrogens on the left, 14 hydrogens on the right, 3 mercury on the left, 3 mercury on the right, and don't forget to check the charge. The total charge on the left-hand side, -2 plus 14, positive 12. Right-hand side, 6 plus 6 plus, positive charge. We're right. We must be right. Now, you're reassured if you're right. If you're not right, what do? Well, here's what you don't do. You don't give up. If it's not balanced, see if you can find your mistake. Work in pencil. You're not afraid to make a mistake. But if you can't find your mistake, here's what I suggest for this problem especially, but also for other kinds of problems. Take a break and then start the problem over from scratch on a separate piece of paper. You're unlikely to make the same slip of the pencil independently both times. All right, so that's the picture. Let's see if we can practice. And you're going to try to get ahead of me a little bit more every single time. So here's my next redox reaction, and I can tell it's redox because on the left I have elemental chlorine, no charge, oxidation number 0. And the chloride ion is a -1, so the oxidation number changes. This is a redox reaction, and I'm going to apply the routine. The first step is to break it into 2 half reactions, and I think that's the new challenge in this problem. I'll get you started with that. In my first half reaction, I'll have chlorine becoming chloride in the first half reaction. The second half reaction makes hypochlorous acid, which is not on the list of things I expect that you know. But what's the reactant for it, that second equation? It must be Cl2, right? What else can it be? So yes, the same species can be the reactant for more than one half reaction. Now that I've got you started, I would love it if you would finish this yourself. And in these early stages, you'll probably need to keep that list of steps beside you in your pre-lecture notes. Go ahead, balance the equation, and pause the video. All right, I'm back. I'm going to go through the steps without flashing back and forth this time. The next big chunk is to balance the atoms. And there's a particular order that I do that in. Everything but the hydrogen and oxygen, then the oxygen, then the hydrogen. So first half reaction, 2 chlorines on the left, 2 chlorines on the right. The atoms are balanced. Second half reaction, 2 chlorines on the left, 2 chlorines on the right. Now my chlorines are balanced, just not the oxygen and the hydrogen. So the next step is to balance the oxygen. And we're assuming we're in aqueous solution, so we're going to balance the oxygen with water. I'm going to put 2 water molecules on the left-hand side. And let's double check. 2 oxygens on the left, 2 oxygens on the right. Good. Final atom to balance, hydrogen. We're going to assume we're in acid until the evidence slaps me in the face to the contrary. I'm going to balance hydrogen with H+. On the left-hand side of the second half reaction, I've got 4 hydrogens. I've only got 2 on the right-hand side, so I'm going to need 2 more hydrogens in the form of H+. Check early, check often. 4 hydrogens on the left, 4 hydrogens on the right. So we've got the atoms balanced. The next thing we want to balance is the charge. Don't forget the charge. First half reaction, total charge on the left, 0. Total charge on the right, -2. The difference between 0 and -2 is 2 electrons. Now here's the part where we got to pay attention. Which side do the 2 electrons go on? I'm going to try them here on the left-hand side. And I'm going to double check. Total charge on the left-hand side, -2. Total charge on the right-hand side, -2. Equal charge, good. Charge is balanced. All right, on the second half reaction, total charge on the left-hand side, 0. Total charge on the right-hand side, 2+. Difference between 0 and 2+ is 2. I'm going to add 2 electrons. To which side am I going to add them? This side over here, and double check. Total charge on the left is 0. Total charge on the right is 0. I also see that reassuring thing. Electrons in on the left-hand side, electrons in the first half equation, electrons out in the second half equation. They should always be on the opposite sides. All right, the purpose of all that so far was to balance half reactions. Now that they're balanced, we can combine them back together. But remember, I need the same number of electrons into one and out of the other. I shouldn't see electrons in the final equation. Your list of steps would be to balance them by to multiply the half reactions by an appropriate factor so that it is the same number of electrons on each side. But we don't have to do that this time because it's 2 electrons in both. So I'm ready to move ahead just to adding them together. The last time I showed the electrons explicitly, but now I'm going to cancel them out early on. 2 electrons on the left, cancel 2 electrons on the right. Here we go. I've got 2 Cl2 molecules plus 2 water on the left-hand side when I add it up. On the right-hand side, I've got 2 chloride plus 2 HClO plus 2 H+. And the most important step, check and see if it's balanced. There's no reason to be insecure that you've made a mistake. You can know. Check for balance. On the left-hand side, 4 chlorines. On the right-hand side, oops, I didn't do that on purpose, but I forgot to bring down that 2. I caught it when I checked it. Whew. All right, now we're going to check for the hydrogen balance. 4 hydrogens on the left, 4 hydrogens on the right. Good. Oxygen. 2 oxygens on the left, 2 oxygens on the right. Good. And don't forget to check the charge. Total charge on the left-hand side, 0. Total charge on the right-hand side, -2 + 2, 0. We must be right. Now this is an acceptable answer, but I'm going to make one more change. In general, we show the lowest possible stoichiometric coefficients. I've got a common factor of 2 for all of those, so I'm going to divide everything by 2. And I am left with my balanced redox reaction. So far, so good? All right, let's try one more together. You'll need to practice on your own to get secure, but let's try one more together. The new twist I'm going to throw into this one is that we're going to do it in basic solution. But before I set you off to do it on your own, we're going to do this as if we're balancing it in acid first, and then we'll come back together and I'll show you how to modify it for base. So I want you to balance this redox reaction in acidic solution. Go ahead, pause the video. All right, here I go. First step, break it into 2 half reactions. All the chlorine containing species in one, all the manganese containing species in the other. Now I have to balance each half reaction. First, I'm going to balance the atoms. I'm going to balance the atoms other than hydrogen and oxygen first. First half reaction, 1 chlorine on the left, 1 chlorine on the right. Done. Second half reaction, 1 manganese on the left, 1 manganese on the right. Good. Second step, balance the oxygen with water. First half reaction, 3 oxygens on the left, so 3 waters on the right. Double check, 3 oxygens, 3 oxygens, good. Second half reaction, 2 oxygens on the left, 4 oxygens on the right. So I'm going to need 2 water molecules over here. Double check, 4 oxygens on the left, 4 oxygens on the right. Good. Now we're going to balance the hydrogen with H+. In the first half reactions, I see 6 hydrogens on the right, so we're going to need 6 on the left. Double check, 6 and 6. Good. Second half reaction, 4 hydrogens on the left, so I'll need 4 H+ on the right. 4 and 4. Good. So the atoms are balanced. Don't forget to balance the charge. We balance the charge with electrons. This is an electron transfer reaction. First half reaction, on the left, -1 + 6, that's +5 altogether. On the right-hand side, -1 altogether. The difference between +5 and -1 is 6. And which side am I going to put the electrons on? I think I'm going to add them over here. Now we'll double check. Total charge on the left, 6 negatives and another negative, -7, + 6, -1. On the right-hand side, -1. Good, same charge on each side, balanced. Second half reaction, no charge on the left. On the right-hand side, I've got a -1 for the permanganate, +4, that's +3 overall. The difference between 0 and +3 is 3 electrons. And where do they go? I hope they go on the right-hand side, because they were on the left-hand side in the other reaction. Let's double check. Second half reaction, total charge on the left, 0. Total charge on the right, -1 + 4 is +3, -3, 0. Good, the charge is balanced. Okay, my half reactions are balanced. So now I'm going to add them up. But before I do, I have to make sure it's the same number of electrons out of one that goes into the other. So I can see that I will have to multiply that second half reaction by 2, so that we get 6 electrons out. But remember, that multiplies everything in that equation by 2. All right, now here we go. I'm going to add it up. And I choose not to show the electrons anymore. I know they cancel out. I made sure that they did. But if you want to see them, you do what you need to do to get that confident feeling you want to have. Here I go on the left-hand side. ClO3 minus plus 6 H pluses plus 2 MnO2 plus 4 H2O. And on the product side, chloride plus 3 waters. And remember, we're doubling everything in the second half reaction. That's 2 MnO4 minuses and 8 H pluses. All right, that's good. But I'd like to simplify that. A chemical equation shows only what changes. So I'm going to cancel out anything that's the same on both sides. I see H plus on both sides. I'm going to cancel 6 H pluses from the left and 6 H pluses from the right, and that's going to leave me 2. Similarly, I see water in both the reactants and product sides. I'm going to cancel 3 water from the product and cancel 3 waters from the reactant side. That's going to leave me with 1. That's simpler. Maybe I'll write that out clearly, so it's going to be easier to double check that my equation is truly balanced, which is the last and most important step in balancing in acid so far. Now, I check as often as I can. I'm going to check balance at this stage, even though I'm not done, because eventually I have to go into basic solution. Easier to catch a problem before you perpetuate it, though. Chlorine on the left, chlorine on the right. Oxygen on the left, let's see. 3 and 4 is 7, and 1 is 8 oxygen on the left. 8 oxygen on the right. Good. 2 manganese on the left. 2 manganese on the right. Hydrogen. 2 hydrogen on the left. 2 hydrogen on the right. And don't forget to check the charge. Total charge on the left is -1. Total charge on the right, -1 minus 2 is -3 plus 2 is -1. Same charge on both sides, we're balanced. So we've got an equation balanced in acidic solution, but I want to make it basic. How do I know that it's balanced in acidic solution? I see H+. That's the species I associate with an acidic solution. The species I associate with basic solution is hydroxide. So I'm going to add hydroxide to my equation to neutralize the acid. How much hydroxide am I going to add? Enough to neutralize the acid that I have. So because I have 2 H pluses on the product side, I'm going to add 2 OH minuses. H plus OH minus is going to make water, and that will cancel out, that will get rid or neutralize the hydrogen. Before I do though, remember my equation was balanced before, so just like in math class, to keep it balanced, whatever I did to the right-hand side, I'm going to have to do to the left-hand side. So I'm going to add 2 hydroxides to the left-hand side as well. Here we go. ClO3 minus plus 2 MnO2 plus H2O plus 2 hydroxide gives me Cl minus plus 2 MnO4 minus. Now 2 H pluses and 2 OH minus makes 2 water. Now, are we done? I think I can make it a little better. Now I've got water on both sides. So I'm going to tidy this up by getting rid of one water from the left-hand side and one water from the right-hand side. Here's what's left. ClO3 minus plus 2 MnO2 plus 2 OH minus gives me Cl minus plus 2 MnO2 minus plus H2O. I think I'm balanced in base. How do I know I'm in base? I see hydroxide ions in my equation. But one last double check. Chlorine balance, good. Manganese, good. Oxygen, 3 and 4, 7 and 2 is 9 on the left, 9 on the right, good. Hydrogen, good. Don't forget to check the charge. -3 on the left, -3 on the right. Good. Now that seemed like a lot of work, but no step was any different from the steps you've seen before. Why did I go to all those steps? Well, I think in redox reactions, it's really hard to guess at what the balanced equation is. So even though I showed a lot of steps, at least I got a balanced equation. Take your time, check out early, check often, and get some practice in, and we'll get this covered. So this is the end of our unit on writing equations. When we come back in the next video, we'll switch back to quantitative work. We will use stoichiometry to relate the amounts of different substances.